Uh, Good afternoon, all of you. Today, let us start the discussion. So, so in the last lecture, we learned about the eigenvalues and some eigenvalue problem and how to find them numerically, mainly the power iteration method. So, in this lecture, we will study more about it. Let us just wait, and then we'll start with some numerical scheme that deals with finding the eigenvalues of a given matrix. Today we'll be discussing Gauss-Covalent circle theorem. So the today's topic discussion is Gauss-Covalent circle theorem. As we know, an important tool in eigenvalue approximation is the ability to locate the eigenvalues. For example, in the last class, we discussed power method, and the aim of that method was to find the dominant eigenvalue. Now, naturally, one question can arise that okay, if you are not able to explicitly tell what are the eigenvalues, because eigenvalues carry a lot of information about the matrix, for example, whether or not it is singular and other properties, for example, diagonalizability, all these things can be computed by the eigenvalues. So the study of eigenvalues becomes an important tool in linear algebra as well as in the numerical analysis. So this Gauss-Corin circle theorem tells us that there are certain disks in the plane R2 where this eigenvalue, all the eigenvalues of a matrix will lie. So basically this theorem helps us to locate all the eigenvalues of a matrix. Hence in this way, this theorem is an important part of our knowledge. Should be. So what is the theorem? We'll tell later, but first remark. This theorem helps us to locate the eigenvalues of a matrix this theorem actually this theorem explicitly constructs n disks in the complex plane with centers at the diagonal elements of the matrix. And all the eigenvalues of the matrix lie in the union of these disks. So let us explicitly write what is the theorem. This theorem is called Gauss-Corin circle theorem. So let A be an n cross n matrix, and for each k varying from 1 to this, varying from 1 to n, we define row k as this. It is the sum of all those akj such that j equal to 1 and j will not be equal to k. Okay. So what is this? What is this sum? It is the, loosely speaking, it is the kth row sum, right? Minus diagonal entry. Obviously, we are talking in terms of modulus. And dk denotes the fused disk in the complex plane with center AKK and radius rho k, and that is Z in C, such that so this is a disk centered at AKK and radius equal to rho k. So the conclusion is each eigenvalue of A lies in one of the disks. In other words, in other words, no eigenvalue of A lies in C minus union dk, k going from 1 to n. What does it mean basically? It says that all the eigenvalues lies in this union of dk's. Secondly, suppose that among the disks d1, d2, dn, there is a collection of m disks whose union, let's say denoted by Rm, is disjoint from the union of the rest of the n minus m disks denoted by R2. So we have the Rm, the collection of m disks whose union is disjoint from the rest of the n minus disk, and this is denoted by R2. Then exactly m eigenvalues lie in R1 and n minus m eigenvalues lie in R2. Of course, we are counting with algebraic multiplicity. Counted with algebraic multiplicity. So these disks dk, uh, k varying from 1 to n, these are called the Gauss-Gorin disk. Gauss-Gorin disk. Now, let us prove it. The proof is interesting. We prove only first part because proving second is beyond the scope of this course. So let us see what was the first. Okay, let us let us prove first, then we'll give example. So if you have an n cross n matrix, you compute this row k. Okay, you, for example, row 1 will be the sum of the absolute value of each entry in the first row minus mod a11. Okay, you keep on doing this for row 2, row 3, and so on and so forth. So now consider the disk which centered at the diagonal entry, corresponding diagonal entry, and the radius rho k. So the Gauss-Gorin circle theorem, what does it say? That each of this eigenvalue lie in one of these disks. Okay, so we shall prove this. So let lambda be an eigenvalue of A. Then by definition we know what happens. Then there is a non-zero vector V in Rn such that AV is lambda V, right? Now let R varying from 1 to n be such that VR is actually the infinity norm of V, and what is that? It is the maximum of mod V1 in the maximum of the components of vector V, and this will be strictly greater than 0. Okay, yeah, and we know this will be strictly greater than 0 as V is non-zero. Now if this was your system 1, let's say, then you consider the rth equation of this system. It will be AR1 V1 plus and that is you consider this system AV minus lambda V is 0. So what will be this system? Like the rth equation. Okay, let us write one by one. For example, the first equation will be A11 plus V11, then A12 V2 up to so on and so forth. You will have A1n Bn, then minus lambda 1 V1 minus, sorry, not lambda 1. Yes, if the first equation will be lambda V1, right? So the second equation will be A21 V1 plus A22 V2 lambda V2 and so on and so forth. AN1 V1 yeah. So this will be it. So the rth equation, what is the rth equation? Rth equation will be AR1 V1 plus AR2 V2. Somewhere here you will have AR, R, VR, and so on and so forth, AR and VN. And you will have lambda VR here. So this will, you take that right hand side to the left hand side, and you will have AR1 V1 plus AR2 V2. Here you will have AR R minus lambda VR, and everywhere else you will have the same thing, no change. So this will be 0. Now since see we are okay, since this value is non-zero, so this implies ARR minus lambda BR is actually minus AR1 V1 minus AR2 V2, okay, and up to so on and so forth. You'll have AR R plus 1 VR plus 1. Okay, let us put in the plus in the bracket plus AR and VN, right? Now, if you take the minus here, and because VR is non-zero, we can always divide. So you have V1 by VR, AR1, V2 by VR, AR2, VR plus 1 by VR, ARR plus 1, plus so on and so forth, plus VN by VR, ARN, right? Now, you can use triangle inequality. You can use the triangle inequality, and what will it give you? So you have mod here, then it will be less than equal to mod of this times mod of this, right? Yeah. Now you see the way this is chosen, the way your VR is chosen, because see mod Vj is less than VR, right? Because it is, yeah, the way we have chosen R. So, and this is this. But what is this? This is precisely rho R, right? This is precisely rho R. So what have we proved actually? So we have proved that lambda belongs to dr, right? And this was what we had to prove. Just a minute. So we have proved that lambda mod of lambda minus ARR is less than equal to rho r. That is, lambda belongs to dr. Yes. So hence this was the proof of Gauss-Gaussian circle theorem. Now let us see some example of what is happening. You take this matrix A, 4 0 minus 2, 1 2 0, and 1 1 9. So the Gauss-Gaussian disks are given by, for example, D1. What will be D1? So it will be Z belongs to C such that Z minus 4 is, you just add modulus of these two, right? So it will be less than equal to 2. Yeah. D2 will be Z belongs to C. The diagonal entry is 2, right? So it will be Z minus 2 less than equal to 1. And D3, it is what? It is basically Z minus 9 less than equal to 2. Okay. So if on the number line you draw it, on the complex plane, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So first disk is centered at 4 and 2. So this disk, right? Yes. This is the center. The second disk is Z minus 2 centered at 1. Okay, so let us draw that disk. Centered at 2, and yes, so this will be this disk. Yeah. And the last disk will be centered at 9 and radius 2, which means this disk. Yes. So if, okay, let us color coordinate this. So this is your D3, this is your D2, and this is your D1, right? D1, D2, D3. Yeah. So you see that. So what does the second part of, so what does this second part says? So what does Gauss-Gaussian, first thing first, the first part of Gauss-Gaussian circle theorem will imply that all eigenvalues lie in D1 union D2 union D3 and Second, of course, we are saying eigenvalue of all eigenvalue of A. Yeah. And what is the second part? The second part says, suppose that among the disks there is a collection of m disks whose union is disjoint from the rest of from the union of the rest of the disk. Then exactly how many eigenvalues? M eigenvalues lies in that disjoint union. Okay. So by this we have one eigenvalue of A lie in D3, and the other two eigenvalues lie in D1 union D2. Yeah. So few remark. This Gauss-Golin circle theorem is helpful in finding bounds for eigenvalues. Okay. Second, we know that the main disadvantage of power method that we have discussed earlier is that if a given matrix has more than one eigenvalue, has more than one dominant eigenvalues, then the method may not converge. We have seen this, we have discussed this, and we have seen one example. Then the method may not converge. So this Gauss-Corin circle theorem Gauss-Corin circle theorem can sometimes be used to see if a given matrix has a unique dominant eigenvalue. And whether or not the power method converge. Okay. So these are the few remarks. Now, one immediate corollary of the Gauss-Green circle theorem is the following. And this happens because A and A transpose have same eigenvalues, right? So it is Gauss-Green circle theorem for A transpose. So for any, okay, let A be an n cross n matrix for each k equal to 1 to n, define tau k by, now this is the column sum, okay? J going from 1 to n, and j is not equal to k, and dk denotes the closed disk given by, now center is same, but the radius is the column sum, such that z minus akk is less than equal to tau k. Yeah. Then the same conclusion as we have. Number 1, each eigenvalue of A lies in one of the disks Bk. That is, no eigenvalues of A lies in lies outside this union. And that is obviously true because we have seen the Gauss-Green circle theorem. And again, I repeat, this process, this phenomenon does happen because A and A transpose, they do have same eigenvalue. Second, suppose that among the disks b1 b2 bn there is a collection of m disks whose union, let's say denoted by C1, is disjoint from the union of the rest of the n minus m disks. And this is, let's say we denoted by C2, then exactly m eigenvalues lie in C1 and n minus m eigenvalues lie in C2. Of course, the eigenvalues are counted with multiplicity. Counted with multiplicity. So this is C1. So for example, let us try to see what is happening geometrically. You are drawing this, let's say. Some disks are like this. And the other disks are these are like this. Yeah. So if you have 6 cross 6 matrix, then picture might be like this. So then this is your C1 and this is your C2. So this theorem says you will have 3 eigenvalues here, 3 eigenvalue here in this union and 3 eigenvalues here. Okay. Yes. So now let us do some questions. So prove that the eigenvalues of the matrix A, they lie, this is the matrix. They lie in this region. You know. So how do you prove? Let us see. Mm. So, okay, let us see. How do we prove it? One can compute directly, but we want to use Gauss-Gorin circle theorem. Okay, so your D1, it will be Z in C such that Z minus 6 is less than 3. Okay, now D2, Z in C such that Z plus 5 is less than 1. D3, Z in C such that Z minus 4 is actually less than equal to 3. So, you know, so Gauss-Gorin's circle theorem implies that every eigenvalue lambda of A lie in D1 union D2 union D3. Now let us see what is D1. Let us draw the picture again. So you have 1, 2, 3, 4, 5. You'll need some minus here also. Then you have minus 1, minus 2, minus 3, minus 4. You have minus 5 here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. Yeah. Yes. So if you draw, the first disk is 6 with center 3. So it will go till here. It looks like ellipse, no? Uh-huh. Yeah. Then what happens? So this is D1. Then D2 will be centered at minus 5 and the radius 1. Yes. So this is D2. This is D1. Okay. And the last is centered at 4 and 3. Yeah, so this is D3. So in here, so this, what does it imply? If lambda belongs to it, this implies mod z is between 9 and, yeah, no, this implies mod z is actually, you just use reverse triangle inequality. So you will have mod z minus 6 is less than equal to 3, and this will give you mod z less than equal to 9. Here you will have 5 minus mod z, that is less than equal to 1. And maybe, yeah, mod z minus 5 is less than 1. So again, this will imply mod z less than 6. And here what you'll have mod z minus 4 less than equal to 3. So mod z less than 7. Okay. So in all these three cases, you see, even from the diagram it is clear that mod lambda, so therefore mod lambda should be less than equal to 9. Okay. Now how to prove? Now how to prove? Now so it remains to show that mod lambda will be greater than equal to 1. Okay. So you just use reverse triangle. It is clear from the picture, right? If any mod, so this is the, what is the mod? What is this? This is the distance. Mod lambda is what? You have to show that geometrically. What does it mean? Distance of lambda from 0 is at least 1, right? At least 1. So if any eigenvalue lie here, you see the distance is at least 1, and here if any eigenvalue lie, the distance is at least 5. Okay. So in any case, the distance is greater than equal to 1. So let us write that. So let's say if lambda belongs to D1, we do it pictorially, geometrically it is very much clear. Let us just write it mathematically. If lambda belongs to D1, then mod lambda minus 5, then you know this, right? This reverse triangle inequality will always hold, and mod lambda minus 5 is 3. Now what does it imply? It implies 5 minus mod lambda is actually 3. So it has 2 is greater than equal to mod lambda. So hence in this, because 1 is always less than equal to 2, so you have this, right? Now what about, now if lambda belongs to D2, then again you use triangle inequality, and you will have mod lambda plus 5. What did I? Oh, sorry, it should be 6. So it is 3, then 3. Yeah. Again, reverse triangle inequality. My screen just froze. Yeah. So it is given to be less than equal to 1, right? Yeah. So what does it imply? That 5 minus mod lambda is actually 1. So this implies 4 is greater than equal to lambda, and because 1 is always less than equal to 4, so hence this follows. And similarly, now you know how to prove for D3. Then mod lambda minus 4 is less than equal to mod lambda minus 4 less than equal to 3. This is D3, right? So the first step follows from the reverse triangle inequality, and you have this mod lambda. Yeah. So in either case, you have mod lambda is greater than mod lambda is at least 1, right? So hence mod lambda is in between 1 to 9 for all eigenvalues lambda of a. Okay. Yeah. Now, so this you see now this is an annular region, right? This, yeah, this is not now the circle. So we can actually also find annular region for the location of eigenvalues. Yeah. Okay, so we stop here with this linear methods. So the okay, let us see what we have done so far. So we have seen Gauss-Corin circle theorem. Now this theorem helps us to locate the eigenvalues of a matrix, and we know why. They eventually lie in the closed disk, uh, obtained by the kth row sum except for the diagonal entry, and the center is the diagonal entry itself. So you will have picture like this. Certain eigenvalues of eigenvalue, all the eigenvalues of A will be lying in the union of the Gauss-Corin disks. Okay. Then we saw the Gauss-Corin circle theorem for A transpose, and saw some examples that even the eigenvalues can be restricted to have the eigenvalues can be restricted to be in an annular region. Okay, and this annular region is nothing but obtained by the reverse triangle inequality on applying reverse triangle inequality on the Gauss-Corin disk. Now we move to the next part of this course, and this is called the non-linear equation. So we start its discussion today. Non-linear equations. You see, up until now we have been finding roots of a linear equation. Now we'll be having non-linear equation. For example, mm, to find the roots of equation of the form fx equal to 0, where this fx can be anything. Okay, this f, it is just some function given on a closed interval ab. Is a given non-linear function. Now, what do we mean by root? What do we mean by root? That is, to find r in AB such that f of r is 0. Okay. Yes. Now you see, it is well known that all roots of a nonlinear function cannot be solved explicitly to obtain the exact value of the roots. So hence we need to look into the method which will give us an approximate answer to this equation fx equal to 0. It is not always, most of the time actually, it is not possible to find an explicit root of the function, but there are methods which helps us in locating the roots of a given equation of this form fx equal to 0. So in this series, the first method is the bisection method. So we first study the bisection method. Yeah. So how do we do it? If you are given an interval, okay, so given f a to b to r continuous function, we look into the continuous function. So this is a hypothesis, continuous function. We wish to locate the roots of f, function fx. That is to solve the system fx equal to 0. So in this process, step 1 is so define x1 to be the midpoint. So why does it called bisection method? Bisect means to cut something into half. So every time we'll be cutting this closed interval a comma b into half, and we'll be considering the midpoint. So let this be the midpoint of a comma b. So that is x1 to be a plus b by 2. So on the number line you have a situation like this. You have A here, you have B here, you have x1 here. Okay. Now you see exactly one of the two things happen. Now, exactly one of the following two statements hold. First, either f of x1 is 0, right? Then in this case, we are done. So this is the root. Then we are done. Or second, either f of ax1 is negative. Just a minute. I am forgetting something. Yeah, sorry. Yes, and yeah, so this needs to be written down. Otherwise, so there is one additional assumption that f of a times f of b is negative. So what does it mean? It means that f of a and f of b have opposite signs, right? Have opposite signs. Okay, I will only. So when that happens, when this happens, on A, this is your A and this is your B. It has opposite signs. So let us say this is negative and this is plus. F of A is negative. Okay, we need to draw a graph to explain it better. Yeah. So if you look at the graph, let's say this is your A and this is your f of A. This is your B, and let's, because these are opposite signs, so one has to be in the positive y-axis and other will be in the negative axis. Such that, so you cut down this part ax1, you cut down this part, you bisect this interval a comma b and consider it midpoint to be x1. Now you see at a, we are just fixing one thing. Okay, at a, let's say this was positive, f of a, the value of f, and this was negative. So if x1 is non-zero, if f of x1 is non-zero, okay, if f of x1 is non-zero, then either this will have a positive value, f has a positive value at x1, in which case the root will lie in this interval. If negative, then root will lie in this interval. So we can always cut down the length of the interval by half to locate the root, and we do this in continuation, okay? Yeah. So this is called the bisection method, and this is basically an application of the intermediate value theorem. So either f of a f of x1 is non-zero or f of b times f of x1 is non-zero. So if case 1 holds, that is f of x1 is 0, then we are done, right? In case 2, in case 2, if the first thing happens, f of a f of x1 is 0, then what happens? Then again by intermediate value theorem, uh, fx equal to 0 has a solution in this interval a comma x1, right? And second, if second thing happens, if b of x1 is, this product is non-negative, then f of x equal to 0 has a solution in b comma x1, x1 comma b. So you started with, a comma b, and then you cut it down into half, you know, a comma x1 and let's say this is x1 comma b. So what do we have? So if this length is 1 at this stage, what is the length of the interval at this stage? B minus 2, b minus a, sorry. And here both the intervals have length b minus a by 2 because x1 was the midpoint, right? x1 was the midpoint. Yeah. So at this stage you will find one interval. So what we have, either the solution is here fx equal to 0, either there exists x here or there exists x here, fx equal to 0. Okay. Now you see at this stage we have already have an interval smaller than the previous one. So it is a success in the sense, up until now we were thinking, okay, the roots is in the interval a comma b. After going to step 1, after completing step 1, the intermediate value theorem guarantees that you can find the root in half of the length in the interval which has half of the length as the previous interval. So let's say if root is here, okay, without dose of generality, then again you again split it into half, okay. Let's say this time the midpoint is x1 x2. यहाँ पर x2 is, here the x2 is x1 plus b by 2, or x2 is x2 comma b. Again the root will lie in some interval, right? So let's say let's say root lies in here. Then what do? You again then you again split it into half. So at this stage, what is the length? At this stage the length was b minus a by 4. So then you will have x1, x3, something like this. I'm just writing it roughly so as to make you understand what is happening. Then x3 to x2. Yeah. And here the interval is the length of the interval is b minus a by a, because at every stage the length is reducing to half. So you keep on doing this. You keep on doing this, and ultimately you will have b minus a by 2n, right? So we are getting a sequence of interval. We are getting a sequence of interval. Let's say a naught b naught to be our ab, then a1 b1, then a2 b2. You keep on doing this. This is our actual interval. Continue doing this. So the length of each interval is b minus a by 2n, right? And this goes to 0 as n goes to infinity. So which means eventually this will end at x, right? Where x is such that f of x is 0. Eventually you will be having a single point if you do it infinitely many times. And this is precisely the idea of the bisection method. So I will write the theorem now. This is the idea. Theorem. Convergence and error estimate of bisection method. So let's start from here only. Let f be a continuous function on a closed interval a naught comma b naught, and it is real valued. Such that f of a naught times f of b naught is negative. This assumption is necessary so as to ensure by intermediate value theorem that the root lies in this interval a naught, open interval a naught comma b naught. Then number 1, there exists an r in a naught comma b naught such that f of r is 0 and the iterative sequence of midpoints, the iterative sequence xn to be an plus bn by 2. Oh, sorry. An plus bn by 2. This is the sequence of midpoint. The iterative sequence of midpoints converge to R. Second, for each m, you have this error estimate also for uh, yeah. We have the following error estimate. What is the error estimate? So this was the sequence, and minus this XMN. These are the approximate values of the root, and R is the real value. So the difference between them is the error, and this is precisely half n plus 1 times b naught minus a naught, and this we know why, right? Yeah. And you see this goes to 0 as n goes to infinity. This is just a remark. Yeah. So proof, you just see. Okay, then we see some example on dissection method. Yeah, okay. So let us see some example. Mm, just a minute. Yeah, okay. Screen again froze, so let us go. Yeah. So to start with a simple example, let us say you have to find this. You have to find an approximate root of this function sin x plus x squared minus 1. And you have to find the root. So the answer is, the question is find an approximate root of fx using dissection method such that The resultant absolute error the resultant absolute error is at most 0.125. So how do we prove it? So to apply the bisection method, first we need to choose an interval a0 comma b0, right? So to apply the bisection method, we must choose an interval a0 comma b0 such that the function fx equal to sin x plus x square minus 1 satisfies the hypothesis of bisection method. So to start with, okay, you just see f of 0. What is f of 0? It is minus 1. And f of 1, it is sine 1, right? And sine 1 is strictly positive. Because sine is positive between 0 to pi by 2. And pi by 2 is greater than 1. So sine 1 is positive. So hence, thus, f satisfies the hypothesis of bisection method in the interval 0, comma 1. Am I correct? 0, comma 1. Now, in order to achieve accuracy, we should be first sure how many iterations we need, okay? So, in order to achieve accuracy, or rather, write it as in order to achieve the required accuracy, we should first decide how many iterations are needed. Okay. So if you use this, so you see we need an accuracy such that xn minus r is less than epsilon. Okay, so then by the estimation of bisection method, we are sure that this will be less than epsilon whenever half power n b naught minus a naught is less than epsilon, right? So this implies, because b naught minus a naught is 1 here, so half power n is less than epsilon. Now if you take log both sides, so you will have ln 1 by half, and this is 0.125. So less than, because log is an increasing function, so inequality will be same because ln is increasing. So yeah, so this is actually ln 0.125 upon log half, and if you compute it, this will be 3. And because ln is, log is negative, okay, this ln half is actually minus ln2, which is negative, so inequality will change. So we need this much. So this shows that, thus we have to compute till x3. Okay, now we know how many iterations we need to compute, so we will do it now. So iteration 1, you see we have a naught is 1, a naught is 0, and b naught is 1. So thus x1 is the midpoint, right? So it will be 0.5. And since we just computed f of x1, it will be sine 0.5 plus 0.5 square minus 1, and it is minus 0.27, which is negative. So f of 0, you see, so here we have this. You have 0, you have 0.5, and you have 1. Now on f of 0, see, this f was negative, f of 0 was negative, f of 1 was positive, and f of 0 minus 1 is negative. So we know the root by intermediate value theorem, it will lie in this interval. Okay. So this is my x1. So iteration 2. Let us go to iteration 2. So what is x2? x2 will be 1.05 by 2, right? And it will be 0.75. So x2 will be here, right? The midpoint of this. And you see f of x2, if you compute and this will be 0.25, which is negative. So you draw the picture again. Now you have, okay, x1, x2, 1, and negative, negative, positive, positive. So again, by intermediate value theorem, so the root will lie in this interval. So now we need to compute as a third iteration. Here you will have your x3. Okay. Iteration 3. Iteration 3 is x3. What it will be? It will be the midpoint of this interval x1, x2. And what is x1? x1 is 0.5 and x2 is 0.75. So its midpoint will be 0.5 plus 0.75 by 2, which will be 0.675 or 625. And if you compute f of 0.625, it will be, we don't need to compute it, right? We just need to find the third iteration. So in fact, the exact value of the root r is somewhat equal to 0.636733. This is the true value of root r. And if you take the absolute value, the error between xr minus r, it is precisely 0.011733, and it is strictly less than 0.125. This is what we wanted, okay? But there is a catch, however, if you see, the required accuracy is also obtained at x2. That is, you compute x2 minus r, and it is approximately equal to 0.1133, which is strictly less than 0.125. So yes. So you just see this example. So this was an interesting example. Yeah. So in this example, we see an application of bisection method via this example. And not only that, not only we find an approximate root of fx using the so-called bisection method, we also find the approximate root with a certain error estimate condition, and that is that the resultant approximation should be such that the resultant absolute error cannot exceed 0.125. Okay. Yeah. So we end today's session with few comments on bisection method. Remark. The first remark is, This is an important remark actually. Let f and the interval a naught and b naught satisfies the hypothesis of the bisection method. So the remark is, even if fx equal to 0 has more than one root in the interval a comma b, the bisection method has the root it tries to approximate. So it basically means even there are more than one roots. It so can happen that for a given function f, for a given continuous function f on the interval a naught comma b naught, you have more than one root, right? For example, you choose sin x and interval to be 0 to, let's say, 4 pi. Then you have root at, okay, let's take minus 2 pi to 2 pi and sin x. So this has root at 0, pi and minus pi. So it so can happen that in a given interval, in a compact interval, a continuous function have can more than one root. Even then, bisection method has a success rate. Okay, does not fail. It just what interval you start with the beginning. Okay, the bisection method will have the root it tries to approximate. Yeah. So the only draw, one of the main drawback of the bisection method. So this is remark one. Now remark two. Choosing an interval a naught comma b naught such that f of a naught times f of b naught is negative. We know it is very crucial to bisection method. It is very important to find such an interval, right? And what is the process to find such an interval? You just check the product to be negative, which means that f is taking the opposite signs. However, however, there is no general procedure to find such an interval. Okay, so this is one of the main drawback. So we can call it drawback. So this is a drawback of the bisection method. Yeah. So in the next class, we will discuss. What we have in methods of the type bisection method, we always need to start with an interval which already has a root of the given function. So, and this is a very important step to initiate this method. But however, this is not always possible to find such an interval. The function can be very ugly. Okay, uh, which makes it more challenging to find such an interval. But there are other methods called secant method and the Newton-Raphson method, which overcomes this difficulty, and they are called open domain methods. For example, this bisection method is known as closed domain method because you need a closed interval to start with. So we'll see Newton-Raphson method, secant method, their drawbacks, and hypothesis and conclusion in the next session. So maybe we still have some time left. So maybe we can do one more question. So, with this, we finished the lecture. We have discussed quite a few questions. Yeah. So, this non-linear equation we have seen bisection method, and as discussed, we'll be discussing Newton-Raphson and secant method in the next class. But majorly this questions, this is the number of disks. Sorry, the region, the disks where all these eigenvalue will of a given matrix will be lying. And this is precisely the Kerr scoring circle theorem is all about. And how do you obtain that disk? That is precisely the challenge. And the disks are nothing but you just fix, for example, the first disk will be given by you add all the absolute sum of the first row except for the A11 entry. So that will be your radius. And A11 itself will be the center. For the second disk, you go to the second row, you add all the absolute value of the entries in the second row except for the A22 entry. So that will be your radius, and A22 will be your center. And you keep on doing this. So you will have n many disks. There here n is the size of the matrix. So Gus-Goring circle theorem says that each eigenvalue will be lying in the union of these n many disks. Okay. We actually provide a proof, but the proof is easy. This is not difficult. Then we saw some example. In this example, we could draw. The good thing about this Gus-Goring circle theorem is geometrically we can see what is happening. Okay. So this is the first example that we started our journey with in learning the Gus-Goring circle theorem. Then there are some As usual, there is a Gus-Gorin. The good thing about Gus-Gorin circle theorem is that it can overcome the main disadvantage of a power method. Okay, because Gus-Gorin circle theorem helps us to locate the eigenvalue. So it might help us to locate the unique dominant eigenvalue. Okay, which was the main and whose existence must be ensured to begin the power method as seen in the last session. And because A and A transpose have same set of eigenvalues, why? Because their characteristic equations are same. Yes. So because we are working over real metrics, that is why. So Gus-Gorin circle theorem can be applied to A transpose. Now in this case, you have to take the column sum except for the row sum. So that will be your radius, and center will be same. So centers for Gus-Gorin disk for A and A transpose are same, but the radius are changing. For A, it is the row sum except for the diagonal entry, and for the column, for the A transpose, it is the column sum minus the diagonal entry. The conclusions are same. Okay. Yeah. Gus, we saw one question where Gus-Gorin circle theorem can help us to locate not in the disk, not only in the disk but also in the annulus, and for that we use the reverse triangle inequality. So Gus-Gorin, though it gives a disk, but it can also be utilized to provide us the annular region where the eigenvalues will be lying. Then we move to the non-linear methods. So the aim of so far we have seen this solve the system of linear equation. Now the next natural step, because many of the phenomena practical applications can be explained by the non-linear equation rather than linear equation. So it is important to study non-linear equation. And what are they? They are just fx equal to 0 where f can be any function, any non-linear function. For example, sin x. Sin is not a linear function. So to solve such a system, we saw one method which is called the bisection method. Okay. And it starts, so bisection method is basically an application of intermediate value theorem. What does an intermediate value theorem say? It says that whenever you have a continuous function on a complex set, and at n points one is taking positive value, the other is taking the negative value. So in between there will be at least one C that will have that will make this f 0. That is, f evaluated at that point must be 0. And this is precisely what bisection method takes advantage of. Okay. So let's say you have ensured that there is one root that will be lying in the closed interval. That will be lying in the closed interval a comma b. Yeah. Okay. So many things I have. Yeah. So you just take x1 to be the midpoint because there will be some root between a and b. We don't know. We don't know that root, obviously. So you just take the midpoint and you keep. So now at x1, either it will have a positive value, f will have a positive value, or a negative value, or zero value. If it has zero value, then we are done, right? Just a minute. Yeah. So if at x1 f has zero value, then we are done. If not, then either the root lies in a x1 this interval or x1 comma b in this interval. Let if possible the root lies in x1 comma b. So first of all, what is the length at this stage of both the intervals? It is the half of the previous one. That is b minus a by 2. So now you can apply the bisection method to x1 comma b, right? Again you will get two intervals, and again you will get two intervals. You keep on doing this, and you will have a series of intervals, sequence of interval, and each midpoint will give you a sequence which converges to the actual root. Okay, and this is precisely the theorem that converging. So this is the bisection method, and in the next class we'll see Newton-Raphson method and so other methods also.